Welcome back, everybody. The first speaker of this afternoon is another of Bart's PhD students. The very first to graduate here in Eindhoven, Dr. Remco Duits. And now he is an associate professor at the Department of Mathematics here in Eindhoven. Remco?
Thanks. First of all, it's a real honor here to give a presentation on a mathematical framework, Lie group analysis for medical image processing. And I'm very honored here, especially of the nice day for Bart. Okay, so I will present a mathematical framework, but I won't bother you with too much equations. I will start off with some applications. So let us have a look at the medical imaging problems that we would like to that we consider and that we would like to tackle. So here on the top left, you see an optic image of the eye. And here we see the vascular tree that we would like to automatically detect and analyze for the early diagnosis of diabetes. So it's an optical image here. And here you see an MR image, an MR angiography image, maximum intensity projection. And there you see the 3D blood vessels, the vasculature connected to the carotid vessels. And it is very important to enhance and to detect this complete vascular structure, because this is important for surgery, plaque removal, or intervention stenting, as you can see here. Here you see some X-ray applications. So here on the left you see an X-ray image of the prostate, and here you would like to find the main feeding vessels, basically, so that you can embolize them. Here in the middle, Marcel already gave an explanation on the abdominal aorta aneurysm treatment. This basically an 3D X-ray. It's a very noisy X-ray because you want to do this intraoperatively to avoid mismatch between the fluoroscopy images and the high-resolution CT. So you get basically quite noisy images, and then in these noisy images you would like to enhance and detect the 3D vascular tree here. So in particular the renal arteries in the area of the abdominal aorta. Then here on the image on the right you see a 3D rotational angiography image. And there you see artery-vein malformation. You see that artery and veins are cluttered up in a spaghetti type of structure. And yeah, it's very hard to identify where the blood vessels go. So in all of these problems, they have in common that we need to enhance and detect complex vascular structures, including crossings, bifurcating, and kissing vessels. So in many medical imaging applications, here you see also diffusion-weighted MRI, as also addressed by Luc Florac, where you would like to identify neural fibers in brain white matter to quantify structural connectivity. You can see you have these elongated structures, and typically with all these medical images, you would like to reduce the radiation dose, not to harm the patient, and at the same time, so that's why these images get of low contrast, and it gets hard to automatically detect these elongated structures. And on top of this, these elongated structures, they exhibit many crossings and bifurcations, so really complex structures that you have to deal with. Now, the current methods often fail at crossings and bifurcations. And this gives a costly increase of user interaction in tracking tools for computer-aided diagnosis and therapy planning. So we would like to tackle this problem of dealing with all these geometrically complicated structures, these difficult crossings and bifurcating structures. And the key to the solution is to extend the image domain from position space only to position and orientation space. We do this by means of an invertible transform that does not tamper the data evidence, a so-called invertible orientation score, And then instead of directly processing the image over here, because of the invertibility of the map, we can design the operators on this new space of positions and orientations. So why would you want to do that? For example, here on the left, we see a crossing here, a complex structure here. And you see that all the elongated structures that are involved in such a complex structure, in such a crossing, are manifestly disentangled in the position and orientation space. So there are no crossings if you enlarge the domain of your images. This is useful for crossing preserving diffusions. If you do a nonlinear diffusion directly on the image domain and you put a high diffusion time, then typically you get these artifacts because it's steered by the direction of the gradient in the image, and this is not a well-defined feature there. So you get artificial patterns. Whereas if you do the diffusions, the flows in this extended space of positions and orientations, then these particles cannot collide, and then we get a good enhancement. So it's useful for denoising via crossing preserving diffusions, for example. But it's also very useful for correct tracking of blood vessels or elongated structures in general at such crossings and bifurcations. So for example, here you see a 2D X-ray angiogram for containing coronary arteries. And then the problem is, if you use an industrial tracker, then you see that the industrial tracker typically fails at the crossing over here. So basically the tracker should have followed this blood vessel and it takes this wrong exit. Now, if you go to the orientation score domain and to the space of positions and orientations, you apply the tracking over there. There are no such things as crossings, and you get basically a solution to this problem. And this is just one simple example, but we test it on large data sets where each time we get very good results with our methodology. Okay, so image analysis via invertible scores. So here is basically you see some images, and instead of directly processing the images, we create a multi-orientation distribution of this image, an orientation score, an invertible orientation score. Then in this new image representations of positions and orientation, so this is a 2D image, and then here the positions and orientations here is a 3D volume. Then in this volume, basically, we apply geometric control and track the blood vessels along globally, minimizing geodesics. And then, yeah, you don't suffer from all these problems at the crossings and the bifurcations. Below here you see 3D images, low contrast. Here you see, for example, the renal arteries of the 3D X-ray images. And then we have crossing or geometry preserving diffusions in position and orientation space. And that allows you to denoise these images, get a much clearer view on the blood vessels here, while basically keeping the vessel widths and also to keep track of good contrast and noise ratios. And we compare it to many other methods in the literature, and we do a better job there. Okay, but okay, it's nice to do the processing on position and orientation space, but then you have to employ the Lie group structure in this new representation. You have to think in a moving frame of reference. There is a torqued and curved, we recognize a torqued and curved structure in this new representation. So instead of working with normal derivatives, we work with so-called left invariant derivatives, a moving frame of reference. Because if I go up in the orientation score, I have to twist. Then we use this left invariant vector fields for basically waveform propagation. This is just the iconal equation, but then on this higher dimensional manifold for a waveform propagation, and then backtracking, where we get viscosity solutions, and then the backtracking will give us the global minimizers of the geometric problems. They are also used, these left invariant derivatives, for diffusions, sharpening of the data, and of waveform propagation. Okay? So let us have a look at tracking first. So data adaptive geodesic tracking and orientation scores. Well, suppose I have a car path here. I can lift car parts to position and orientation space, where the height is basically the orientation of the car. The car only has two controls. You can hit the gas, you can turn the wheel in a three-dimensional space. So that means that you have only two controls. That means that you have to apply a sub-Riemannian structure on this space of positions and orientations. Then there are some costs for hitting the gas, turning the wheel, and then you find the global minimizing curves connecting to points and orientations in this lifted image representation, as you can see over here. Okay, so why do we do this? Well, I already mentioned we can deal with the complex crossings and bifurcations where the standard methods in the image domain, they completely fail. So for example, if I have to go from A to B, then you can see that here, when I do a standard waveform propagation directly in the image domain, and I do a gradient descent, then I get the wrong track. If I go to the lifted space of positions and orientations, do the tracking over there, do the waveform propagation there, and then the steepest descent in the lifted space, and then project back these paths, and I don't respect this geometry on the so if I treat that as a normal Euclidean space, I get some better results, but still some side jumps. However, cars have only two controls. You can turn the wheel, hit the gas, but they cannot step aside. And then if you do the processing in the orientations course, then typically you follow the correct vessels. So here are some animations that show what goes wrong if you do directly basically a waveform propagation in the image domain and then a backtracing. This is a partial solution to that. You make an orientation score, you do the tracking over there, but you basically allow these cars to step aside, which you shouldn't. You should use this sub-Riemannian geometry. And then, if you do that, then typically you automatically track these vessels correctly, as you can see here with the Ferrari. Luigi only like the Ferrari. But even these Ferraris have a problem. Sometimes, I mean, you have this when you go to the supermarket, you have to park your car. Sometimes it's better to put your car in reverse. So the global minimizer tells you, hey, you have to put your car in reverse. And this is annoying, because at these bifurcations, you get these artificial motions here. I mean, it's the cheapest path from there to there, but it's not a natural way to deal with all the bifurcations. So therefore, we came up with a new asymmetric Winslow geometrical model on position and orientation space. And then in the optimization, you automatically put at all the bifurcations a key point, an in-place rotation. So this is a globally minimizing solution to the curve optimization problem. And it takes care, it solves the crossing problems and the bifurcation problems. So we get here this extension. Okay, so basically I mentioned why does this work so much better, these trackings? Because we have crossing geodesic fronts. If you do the geodesic fronts in position in the image domain directly, you get leakage at crossings and complex structures. Whereas in the lifted space of positions and orientations, you don't suffer from these problems. These fronts do not leak. Okay, I've shown some 2D examples, but of course in our group we're developing these things in 3D as well. And here you see basically a distribution of positions and orientations in 3D, where for each position you have an orientation distribution represented by an angular profile. And then if we do the correct geometric tracking in this extended space of positions and orientations in 3D, so this is a 5-dimensional space, then, yeah, and we employ the geometry and the sub-Riemannian geometry correctly, then we get good trackings. We don't get these problems that you would have if you would apply Riemannian tracking in the lifted space of positions and orientations. Of course, this was tracking for blood vessels locally. You also would like to get a full vascular tree structure, and for that you have to apply perceptual grouping elements. We do that by clustering techniques in the lifted space of positions and orientations, but not using Euclidean metrics on positions and orientation space, but rather with these sub-Riemannian metrics, where we found very concise analytic formulas to compute these things. And these approximations are good enough in practice, and it allows you to automatically connect the right vessel segments in 2D and in 3D. Then, okay, so part B was to apply geometric preserving diffusions in 3D orientation scores. You can see, if you have these noisy X-ray images, that we really nicely clean up these data sets. We compared it to many other methods, and keeping track of contrast to noise ratios and vessel width preservations, and we get the best results there. So this is on the diffusion systems on positions and orientation space. For the linear ones, I found in the past, together with Marcus van Amsik, exact formulas for these Brownian motions on position and orientation space in 2D. This year, we managed to get the results as well in 3D with exact analytic solutions and the differential geometry of applications. And there are also nonlinear numerical extensions of these via crossing preserving diffusions on 3D images, and would also be very interesting for diffusion-weighted MRI applications. So in diffusion-weighted MRI, basically, it's in diffusion-weighted MRI images, it's very interesting. Luc already addressed this. You can identify structural connectivity between regions in the brain. And this is very important, for example, for surgical planning. So here you see an image where we see the optic radiation. This anatomical bundle is responsible for the visual sight of the patient. So if a patient suffers severely from epilepsy, the surgeon has to cut a certain part of the brain. It's of vital importance that he does not damage these optic radiation fibers. And then, thanks to our methods, we can compute these optic radiation fibers in a stable manner, in a reproducible manner, following a retest procedure. And we verified our methods on pre- and post-operative data. Okay, I'll skip this slide. It's just to show you that these geometric methods on positions and orientations in 3D allow you for a stable extraction of the tip of the optic radiation. And that's of vital importance that the surgeon gets this parameter, the temporal pole to Meyer's loop distance here. And it's done in such a way that if I do a stochastic realization of a fiber tracking, and I do that, say, 100 times, that this identification of this tip does not jump around. And that's where these methods of doing geometric processing of position orientations in 3D allow you to identify this tip in a stable way. So the conclusion: current vessel tracking and enhancement in computer-aided diagnosis tools fail at complex structures. And this can be tackled via orientation scores of 2D and 3D images, where you extend the image domain from position space only to the joint space of positions and orientations. We considered globally optimal path planning in orientation scores, where we can deal both with crossings and bifurcations. What I presented today is a specific part of a new PDE framework on Lie groups via invertible scores. And we have published our results in pure math and applied math journals, but also in geometric control theory journals, and in many applied imaging journals, in diffusion-weighted MRI, retinal imaging, in PLOS ONE, PAMI, IGCV, etc. So it reflects a bit of an ambition in my personal scientific ambition, and I think Bart shares this with me. It is basically the combination of fundamental mathematics and very applied medical imaging that leads to success. And this goes basically both ways. The application requires sometimes difficult mathematical problems that the mathematicians have to solve. And on the other hand, the mathematicians have to listen to what are real-world problems that have to be tackled. I did not present it today, but it's basically currently ongoing. What we do is currently a combination of geometric image processing also with machine learning techniques, and do deep convolutional networks in the orientation score domain. That has many benefits. But finally, and that's the most important thing for today, I really would like to thank Professor Bart Haar Romeny for all the encouragements and his very strong support on this line of research. Thank you very much, Bart.
And thank you, Remco. I think very few of us often encounter the problem of parking our Ferraris at the supermarket, but your point came across very clearly.
So the advice is use a Sedgway, yeah?
So then we continue the line of former PhD student presenters. With Dr. Vesna Prskowska. She is CEO and co-founder of the company Mint Labs in Barcelona. And the company develops a remote medical imaging analysis and visualization platform for the aid of diagnosis and treatment of brain diseases. And as I said, she was a student of Bart, graduated in 2010.
Thank you for the introduction. Just a small correction. I'm not the CEO, but I like the sound of it. So Paolo, watch it. And also recently we did rebranding. So Mint Labs changed the name to Qmenta. So when you see the Q, to know what I'm talking about. It's an honor to be today presenter here. It's a very special day for Bart, and it's a special day also for me to be among old colleagues and amazing speakers. About 7 years ago, Bart handed out the PhD degree, and I couldn't have wished for a better mentor. He's been amazing, very supportive. He's inspirational to all his students. But what is very important is that in this moment, his mentorship didn't stop. He always was having my back, always giving recommendation and encouragement, and always being there to support all of my career steps. Thank you, Bart, for that. But let's go to the talk. The talk is about brain connectivity, about this special organ, this 1.3 kilos of pink jelly that resides inside our skulls. Very protected organ, very important to us. It has over 100 billion neurons, which is 15 times more than the entire human population. And up to recently, there were no ways to non-invasively study this brain. Most of the time, scientists had to basically study post-mortem brains. However, we live in very exciting times, in times of, they call it golden era of neuroscience, or if you're a brain geek, this is the best time in history to be alive. There are a lot of different imaging techniques that can study the brain anatomy and connectivity, and I've divided them by ex vivo. Some like microscale, electron microscopy, axonal tracing. On a mesoscale, these beautiful images of clarity and rainbows that you've for sure seen on the covers of Nature and Science. And macroscale, this is MRI, CT, PET, and so on. All of them have pros and cons, but if we put them somehow as an axis side by side with respect to the spatial resolution, we can see that the ones that are more invasive, they can capture structures on a level of micrometers or even nanometers. However, the non-invasive one, or least invasive, like PET and MRI, their spatial resolution nowadays is in the order of millimeters, but it's improving. I'm a fan of living people and studying living brains, so I'm going to talk today about the in vivo connectivity imaging techniques, and more specifically MRI. When I was preparing this talk, I've been in the field of imaging for quite some time, but I was surprised how recent is this field. Basically, the X-ray and CT imaging were mostly widely used in the 70s, and MRI imaging started in the 80s. The first MRI experiments were conducted in '85, and after that, the birth of cognitive science started. And when we talk about connectivity and connectome, the term connectome was coined very recently, about 10, 12 years ago, by Hagman and Sporns. Even though it's a very recent field, it's a field that is really blossoming, and it has a rapid growth. If I try to explain MRI in one sentence, it would be very difficult, and especially NMR physics. I'm sure that there are people who are much better than me. But I want to quote Niels Bohr, who is a Nobel Prize physicist, and he said, when MRI was born, what these people do is really very clever. They put little spice into the molecules and send radio signals to them. And they have to radio back what they're seeing. Basically, it's oversimplification, but the MRI scanner is radio backing some kind of a signal that we then convert into an image, and then we can do not only powerful visualization, but also a lot of quantitative measurements. So if we talk about the scanner and which sequences can help us to do brain connectivity and visualize it, you can program MRI scanner in many different ways, and you can image many different parts. But for the brain, one important sequence is so-called T1. And this is actually my brain, so now you know my secret. With this sequence, you can see that you can nicely delineate white matter from gray matter. And later on, I'll tell you why this is important, not only for visualization, but also for quantification. Another sequence that I'm an expert in it, that I finished my PhD on, is called diffusion-weighted imaging. And Remco and Luke already talked a little bit about it. But the concept is simple. The math behind is complex. There's a lot of math and image processing. But the idea is that the brain has a lot of water, and this water is diffusing. And in the parts where there's no structure, like the ventricles, it's similar to this glass of water that doesn't have straws on the left side. And there the water diffuses randomly. However, on the right side, where we've put some straws, and this is the analogy of the fiber bundles, the water molecules are hindered by the structure, so they have a preferred direction. So let's say that the MRI scanner is sensitive to this probability density function, and by knowing what are the maximas, we know in which direction there are fiber bundles in this case, or what is the underlying structure. So then we can create these beautiful three-dimensional maps of the brain. This is again my brain, and now you can see that by programming the scanner in a different way and processing the data, we get different information about the tissue. I want to make a disclaimer that in this field, in connectivity, there is a lot of work on local modeling, and in this talk, I don't have enough time, and I've done a lot of work on this kind of glyphs. So this tractography, these lines, as I said, they don't happen magically. There is lots of local modeling, and what we want to do is find the maximas on the glyphs that you see, and then reconstruct the tracks, but that for another talk. For now, let's assume that somehow we can get the information from the T1 sequence, and also we can reconstruct the fiber tracks. And it's very useful, as in this slide, to combine these two modalities, and I'll tell you how you can create powerful mathematical frameworks. The images that I showed you, the spaghetti-like colorful images, are very beautiful, but when you talk to neurosurgeons and neuroradiologists, neurologists, they say that they're not that useful. There is a lot of clutter. So there has been a lot of work done in a way to remove this clutter. For example, in the group of Paul Thompson, Jean et al., they worked on automatic bundle clustering and segmentation, and they used a huge population of about 200 twins to segment these different bundles of interest. This is very important. We've got a lot of clients who want this kind of automatic track segmentation, so we also participated in an ISMRM challenge, and we got a 3rd place, and we have now, we patented this algorithm and preparing a publication on how to automatically delineate these kind of tracks of interest. Why is this important in applications like MS or TBI? What the neurologists want to see is how the corpus callosum or the cingulum or different tracks of interest are different from a normative database. So not only the beautiful visualization, which is also important for pre-surgical planning, but also to derive metrics out of it. And also, when we talk about visualization, one of the I tried not to be biased, and I looked into lots of publications, but many of the beautiful work and important work comes from the group of Anna Villanova and also Professor Bart, basically removing clutter from all these tracks and uncertainty visualization. It's very important that the tracks that we are seeing are the real ones, or to give some kind of confidence interval. So this on the left side is work from Ralph Breheisen, who is sitting over there, on illustrative visualization and uncertainty, where he uses different techniques, but basically with transparency, he's showing the intervals where there is lower confidence that there are fibers. And then Otto, on the right side, does some kind of illustrative visualization, and now we can see that instead of seeing all these spaghetti-like structures, now we can see better the fiber bundles that are in the brain. It gives us better information. And then when we talk about connectivity, there's also functional connectivity. So this MRI scanner is very versatile. So you can program it also to get images for functional connectivity. In this case, what MRI is sensitive is to the increase of oxygen in the blood. So as you see here, two regions, basically we can measure what are the time series while the participants are performing some task or just resting. And then if we want to know if two areas of the brain are working together, if they're functionally connected, we can correlate these two time series. When we talk about functional connectivity maps and visualization in functional connectivity, there's not much state-of-the-art here. This is something that over 10, 15 years has been standard in the field. Normally, like you see on the left side, activation maps are overlaid on a template or in 3D, also on a template brain, which is kind of inflated. These kind of studies are rarely done in individual level, normally are done in a group level where we want to compare patients versus controls for different groups of patients. And also, as you see on the right, Sporns did, and also I did some work on the repetition suppression mechanism in the brain. Once you define which regions are functionally connected, or the brain hubs, you can also visualize them with 3D graphs, but it introduces a lot of clutter. It's not that useful from visualization point of view. And finally, the connectome. This has been a hot topic in the last 5 years or more. The term was coined in a complete analogy to the word genome. The OM emphasized the notion that the brain is a large and unique complex system, a network made of structural and functional connections, edges, linking specific neural units, nodes. So now we can put everything together, all the bits and pieces. From the T1 that gave us good contrast between white and gray matter, we can parcellate the brain in different anatomical regions. From the tractography, we can see how these regions are connected. And if we combine them, then we get the structural connectome, which is basically a two-dimensional matrix. On the other side, with the functional connectome, we know how, from the functional MRI, we know how these different anatomical regions are functionally connected, and they're correlated. And again, we end up with a two-dimensional matrix. And this gives us a beautiful mathematical framework that afterwards we can put every kind of brain, my brain, Professor Bart's brain, everybody's brain in this room as a two-dimensional matrix and analyze it with graph theory. With respect to visualization of the connectome, regardless if it's structural and functional, there are different ways. There are two-dimensional graphs, also three-dimensional graphs, but one of the most useful ways is these circular plots, because they remove a little bit of the clutter. There hasn't been done a lot of work in this field, because at the end is visualization of matrices that are from the range of 100 by 100 regions to sometimes thousands regions. Where is the future going in connectivity visualization? Probably you've seen people sometimes in the malls where they sell electronic gadgets looking like crazy and doing something like this. It's virtual reality, especially now with these portable units like Oculus Rift. It's amazing for gaming. It really puts you in a different reality. It's very immersive experience. But also, many companies already are showing interest to use it not only for pre-surgical planning, but also for education. For example, if you go on the HP website, they already have this kind of initiative to start with education using devices such as Oculus Rift. And of course, we follow the trends, and we also have implemented this kind of visualization in the Oculus, which if you have this kind of device, please send me an email and I can give you a free version. And in this case, one of our developers is literally grabbing the brain and getting with a region of interest, it's grabbing the regions and looking at different fascicles of interest. And you can literally have the brain in front of you. It's very powerful. Another very important trend, if you have been to RSNA, I guess Vito has been recently, 3D printing in radiology is a big thing. And also you can 3D print brains. We've done it in 2013, but one of the most beautiful 3D printed brains that I've seen is the one from the group of Alexander Lehmans. And actually this was done as a sculpture and it was exhibited at the M Museum. This is very important because now surgeons can see the patient's brain. They can hold it instead of visualizing, imagining. They can communicate with each other, but it's also very important for patient communication when they want to explain a procedure, and it's important for patient recovery. Initially, I wanted to finish my talk here and give you all my details if you want to get in touch with me or for any kind of questions. But many people that I met here told me, are you just going to talk about brain connectivity? Can you talk a little bit about what you're doing at the company? So I put quickly some slides, and I really have 5 minutes to explain, to pitch you quickly, what are we doing at Qmenta. Luckily, we recently did this short animation video
can involve many stakeholders and
that
sites,
should explain everything.
thousands of images stored in different locations, many users, and all data needs to be anonymized. All these elements have to seamlessly coordinate to ensure the success of the project. Information exchange and data management becomes very complicated, especially with regulatory requirements. Qmenta provides a cutting-edge cloud platform for streamlining the imaging workflow for clinical trials and research. An all-in-one, secure and compliant solution to store, share, and analyze medical imaging data. Our platform can easily aggregate data from multiple sources and sites in a secure cloud system. You can drag and drop your data right into the browser. Most importantly, Qmenta provides state-of-the-art image processing tools to derive quantitative information from neuroimages with just one click. The tools enable you to quantify changes and gain a deeper understanding of the brain and its diseases. Our SDK even allows experts to develop and share their own tools to run on our cloud system. Using our cloud platform saves you time and money by streamlining your data storage and management, analysis, and collaboration. Qmenta offers an all-in-one solution from imaging to insight for any neuroimaging project, big or small. Visit our website and try the Qmenta platform for free.
So we developed a cloud platform for data storage and also analysis. And we've accomplished a lot since we are established. Basically, at the moment, in 2007, we'll reach 1 million scans, and we're working hard on machine learning with all these scans. We also have very important clients, and we are running our first clinical trials, such as Bayer Pharmaceuticals, Cedars-Sinai, UCSF, and many others. Many clients are in the States, but also here in Europe. And we have a team of currently 23 people, experts in image processing, and also extraordinary advisory board. Walter Gilbert, who is also an investor in the company, he is a Nobel Prize winner in DNA sequencing, and also he's one of the founders of Biogen. Finally, one of the things that I'm really proud is that on this RSNA, Aunt Minnie announced a big award for us as the best new radiology vendor for 2017. And I think I'm even before time, so thank you so much. And don't hesitate to contact me for anything. I really hope that we can have a lot of collaborations.
Thank you very much for these beautiful demonstrations of applied research. And then we go back somewhat in time to early PhD graduations. Professor Weer Niesen graduated with Bart in 1997 in Utrecht. And personally, I say he takes after his mentor, both in enthusiasm and in height. And nowadays, Vero is Professor of Biomedical Image Processing at the Erasmus MC, as well as at Delft University of Technology. And he heads the Biomedical Imaging Group, Rotterdam.
Thank you, Josien. Bart, Hetty, it's an honor and pleasure to be here. You're the reason I'm here, of course, because today is your lecture, but also you're the very reason I'm in this field to begin with. I didn't know about this field before I met you. I was studying physics and I wanted to continue in theoretical physics, but I had some doubt at some points. And then I met Alfons Salden, who's also here. I was doing some work with him. And he said, oh, you have to come to speak with Bart because he has student positions and you're doubting what to do and he can talk to you about the field. So I came to Bart and then exactly what Josien told happened. Bart is so enthusiastic that he told me first the problems here are theoretically at least as demanding as in theoretical physics, which I now know is not true, but at least it was very nice. But it also makes you understand the biology of the brain and you can apply it. So I was sold, I started to work in the field and I never looked back. So thanks for introducing me to the field and making sure that I had something great to do because I think it's a great field to be in. It's also great times and I want to talk about that a little bit today because if you are in the field of medical image analysis or artificial intelligence or mathematics for medical image analysis, I think for decades we've been a promise. We have been a promise and most of the promises we made ourselves. We promised other people we're going to do great things in order for people to fund our research. But if we're honest, it took quite a while before what we were doing was sufficiently good that it's actually going to make an impact on clinical practice, on patient well-being. I think that has been changing because of an enormous amount of work by many people in research, many PhDs, many companies that invested in innovations in the field. And I would like to talk a little bit about the possibilities and the promises of the field nowadays. Because medicine is quickly also turning into a data science in which we're going to use data in order to improve the way we practice medicine for the next generations of patients. So I'm going to talk a little bit about it from the population imaging perspective. I'll explain what it is, but I could also have called it biomedical imaging and genetic or big data analytics for precision medicine, and I will focus on dementia. So first, precision medicine. What does precision medicine mean? The concept of precision medicine is that we try to take individual variability into account when treating a person, when doing a diagnosis, a prognosis, and doing a treatment selection. And most of you, if you are yourself or your parents, get into contact with the medical system nowadays, know that precision medicine is simply not a reality yet. It's a one-size-fits-all, it's trial and error. And imaging and a data science approach can step-by-step improve on that. So what does it mean if we become concrete? Take an example in cardiovascular disease. It's really important in cardiovascular disease to know who to treat. To give an example, if you're symptomatic, and if your carotid artery that feeds the brain with oxygen-rich blood, if it is occluded about 70%, which you can measure, for example, with an X-ray or with a CT or an MRI nowadays, then that is still a marker that is used to do treatment selection. But we know we're over-treating. We're treating about 6 people in order to avoid 1 stroke. And also we miss a lot of strokes. If you look at cancer treatment, we know now that it's much more important what is the biological basis, the subtype of the tumor, than what is the location of the tumor. And in order to select the optimal treatment, we have to identify what particular tumor it is. This is often done with a biopsy, but imaging can increasingly be used to non-invasively determine the type of tumor, and in this way select in a non-invasive way the optimal treatment. And I would like to focus today on dementia. Dementia is an enormous burden on the society, and nowadays it takes on average in Europe 20 months between the moment that someone visits the general practitioner with memory complaints until the definite the diagnosis of the subtype of dementia, like Alzheimer's disease or vascular dementia or Lewy body dementia, is made. So I want to look into dementia a bit more. Dementia is a dreadful disease. I can talk about numbers and costs, but perhaps images tell the word better. So these are images from William Uttermolen. It's an American artist that was diagnosed at 62 with early onset Alzheimer's disease, and he kept making paintings of himself over the years in order to record the progression of the disease. And you see that not only the skills in order to make these drawings, to make these pictures decreased, but you can also clearly see that the mood of him is changing over the years. Now I turn to this very important figure, and it was already shown in the presentation of Professor Marcel Brewer. This is a sort of an hypothetical model of how different markers in our body go up with dementia. So it's based on quite a large body of research, but it's not data on a specific study. But the importance here is if you look at this graph, you can go from left to right in time, and this is about the time that you start to recognize yourself or your environment, that you're not behaving normally anymore, that you have memory problems, that you may have orientation problems. This state is called mildly cognitive impaired. And what's interesting about this graph, that there's a number of markers that are elevated before you enter this stage, which theoretically gives us a window of opportunity to detect the disease in an early stage and look at preventive strategies in order to reduce the chance that this disease occurs. In order to do that, of course, you have to learn from what's happening years before people get the disease. And that's why we're working on population studies in which we image people. And now in the Rotterdam study, we include people 45 years and older in order to understand also what is happening in the years before people have a disease. And this is really important because we have to realize that a lot of the knowledge we have nowadays is very much focused on the moment that already people have clinical symptoms. They go into the healthcare system, and at that moment, different diagnostic tests are being conducted. And that's why the majority of our knowledge resides in the area where people are already diseased. Or in case we're doing screening studies, it may be people at increased risk of disease. So at the moment you want to really understand these years before disease occurs and how disease develops, you have to turn to a cross-section of the healthy population and you have to follow them in time. So this is the design of a population study. Basically, you try to include as many people as you can afford, and you try to measure as many potential risk factors as you can. These can be your genetic predisposition for disease. So in these studies, we are collecting genetic data, but we're also collecting data on lifestyle, whether you smoke, we know what education you've taken, what drugs you take. You could also look at daily activities. You could do all kinds of questionnaires. So you try to collect as much possible information, and eventually you're interested in the relation between these risk factors and the outcome. And the outcome, in the case of neurological disease, could be dementia or stroke. These are difficult studies. These are studies you have to conduct for a long time, because it takes, of course, a number of years before you can differentiate those people that age healthy from those people that contract the disease. That is where imaging comes in. Because if you start then to regularly image people in between, you open up the black box between risk factors and outcome, and you start to be able to relate risk factors to changes happening in the brain. You can relate things that change in the brain to outcome, or you can look at both risk factors and what you see in the brain to see what is the outcome in order to perhaps develop novel prognostic models. So the question is this really an approach that has a chance of succeeding? Is it really an approach that we should be trying to take, to collect a lot of data and hope that in this data there's sufficient information to do some realistic prognostic modeling? So there is now some evidence, and I want to share evidence that was collected by Marius de Groot, a PhD student in our group that won in the journal Stroke the Progress and Innovation Award for this work. And he looked at about 1,000 scans in the Rotterdam study, which were taken 3 to 4 years apart. And he looked specifically at the white matter lesions. Those are these hyperintensities that you see here in the brain. And he was interested to see if you have 2 scans that are a few years apart, And if you see white matter lesions in the later scan, if there was already something discernible in the earlier scan where the white matter seemed to be normal. And therefore he looked at the other MR sequences that were also being taken. The reason for this is that white matter lesions are associated with an increased risk of stroke and an increased risk of dementia. So we use image processing approaches, methods here to register, to spatially map the brain now and 3 years later in a common template space. We use methods to automatically determine and detect the white matter lesions. And then we compare 4 regions. Those regions that were normal at baseline and follow-up, those regions that were white matter lesions in baseline and follow-up, and those regions where white matter lesions had grown or where new white matter lesions appeared. And then we looked at statistics in those regions in order to see whether there was a difference between these regions. And we did that in all the MRI sequences we have. And I'll just show you one example of diffusion MRI that you've seen a lot. Diffusion MRI, the measures that you see can not only be used to construct these beautiful white matter pathways, they also tell you something about the microstructural integrity at a single voxel. So you can make local measures that are somehow related to microstructural integrity. And we compared those measures in the baseline and follow-up scans of those regions that turned into white matter lesions. And interestingly, if you looked at the regions where white matter seemed healthy in the normal scans, at baseline and follow-up, nothing happened. But already at baseline, we saw changes in the diffusion MRI, years before we saw white matter lesions. So apparently there's information in the diffusion MRI data, and we saw the same in the FLAIR images, years before we actually saw the damage on the scans that are routinely used for diagnosis. So what we're currently seeing and using in clinical practice is just the tip of the iceberg of white matter pathology. And it does make sense to look at all the data and see whether we can start to build prognostic models on those data in order to better prognostics in Alzheimer's disease. So we start to do that, and for that we use the whole machinery of automated image analysis that we have. I mean, 10 years ago, we used rule-based systems, then we went to machine learning. Increasingly, we're using deep learning. But essentially, what we try to do is we try to describe the brain of participants in the Rotterdam study as good as possible. In this case, describe the anatomy, the function of the brain, the connectivity of the brain, the presence and the localization of vascular pathologies, etc. So there's a whole pipeline of automated approaches, some atlas-based approaches, in order to generate a quantitative description of all the brains of the participants in the Rotterdam study. So I consider this sort of a library of quantitative imaging biomarkers that describe every single individual. So every single individual is mapped onto a descriptor of hundreds to 1,000 values that says something about the condition of the brain. The question is now then, how can you use this data? How can you translate this to clinical practice? So the first thing we did, we made a prototype, and this prototype was built in order to do something which is very normal in medicine, but which was not very normal in radiology to a few years ago. We were going to use objective quantitative values in reference data. If you take a blood pressure measurement or a serum measurement or even an age and a weight or a body mass index, you always compare the value of an individual to reference data. Now, because you have methods for objective quantification of your imaging data, and if you apply those methods in a population study, you get reference data for imaging biomarkers. So also if you measure something on the brain anatomy, brain function, you can start to relate it to normal values, and in this way compare someone entering the memory clinic with a reference population. So we've implemented this in the Alzheimer's Center Southwest Netherlands, and we're going to evaluate it on about 600 patients per year to see whether a quantitative approach in which next to the normal subjective interpretation of the image, we provide the radiologist with a number of quantitative markers related to reference data, whether that improves their diagnosis and prognosis. We can also go a step further, and Hakim Achterberg, who was a master student here, and through Yale came to Rotterdam, so thank you very much for sending him. He's in the audience also somewhere here. Hakim? Oh, there he is. So, and he will do his PhD defense actually next week. He looked with Marlene de Bruyne, who is sitting next to him. So he looked at, among others, the prognostic value of hippocampal volume and shape for people who developed dementia in the Rotterdam study. And definitely we're not close to the moment yet that we're really, just based on an MRI scan, can really do prognostics, but we can really see there's quite some information in quantifying aspects of the brain in order to stratify for risk for getting dementia. And for example, at this moment, even pharmaceutical companies are already very interested in these results in order to select patients to be included in clinical trials. Of course, imaging is only one aspect of what we can measure from our patients, and there's other pillars of research, people looking at metabolomics, people looking at genetics, often having the same goal. They try to do a better diagnosis and a prognosis of a patient. And actually, imaging starts to play an increasing role in this field because we can start to relate imaging data to genetics data. The concept of genetic studies, of course, very simple. You have somehow your own genetic code, and that determines what you look like and also determines your chances for certain diseases. But not everything is genetically determined. It is essentially a combination of your genetic predisposition and environmental factors which will decide whether you have a chance to have a certain disease. What is very interesting then is to start to relate things that you can see in images that have been linked to disease to your genetic data. And that's, in a population study, is very important because it's much more difficult to find thousands of people with dementia than to find thousands of people with a hippocampus, because we all have two. And then look whether, for example, the size of the hippocampus that has been linked to Alzheimer's disease, whether there are certain genetic alterations that code for that. Now that's called an imaging genetic study. How does it go? This is our genetic code. It's actually a long linear array of letters that can only have 4 values. Before I entered the field, I thought this was just very simple image processing. You know, it's just a one-dimensional image and you have only a few gray values, so this must be much easier than image processing. I now know how complex it is. But initially I thought people are really overselling the complexity of these problems. But the concept of this genetic code is that different individuals may have different nucleotides at certain position. And if that occurs in 1% of the population, it's called a SNP. Now this SNP may be a coding for a disease. It may be, if you have a certain genetic alteration, that you have an increased risk of disease. What we now do, we're not looking at disease, we're looking at an imaging phenotype, for example, the size of the head, and we're looking for those SNPs that code for the size of the head. We do that just by taking all the people that take part in the Rotterdam study, and we make them into groups based on their genetic code. And then we check for the imaging biomarker simply if it's different or not. And in most cases, the imaging biomarkers are the same, but sometimes the group with one variant, clearly the imaging biomarker is different in the one group and the other, and then we say this SNP codes for a larger hippocampus. So very interestingly, this work leads to very new findings. We have a very simple MR scanner. We use very simple genetic techniques, but by doing these studies on thousands of people, we find new genetic candidates, a genetic candidate that is linked to the size of the hippocampus that potentially plays a role in the disease cascade of Alzheimer's disease. So this large-scale data science approach with radiology and genetics is actually steering very basic fundamental research, diving into the underlying genetics of disease. So I think this is very clearly, for example, here we looked at hippocampal volume and we found a new location, and people are diving into this, what may be the relevance of this. Genetics had a promise, like I said, imaging was promising for a long time that it was going to change radiological practice. genetics also had the promise that we could really do very good prognostics. This turned out not to be true, and this, in dementia, this picture explains it. What you're seeing here is, at the moment, all the genetic variations that have been found that give an increased risk of dementia. And here is the dementia of Willem Ettermolen, the artist. It occurs only very infrequently, but it gives a very high chance of getting Alzheimer's disease. But unfortunately, the real epidemic in our society is late onset Alzheimer's disease, and it's caused by many variants that all are very common in the population and that all increase the risk of dementia with just a little fraction. And that shows the enormous complexity of doing prognostics based on genetics and on imaging. And there's really the world to gain still in order to make more out of the knowledge we have here, to turn the fact that we know there's association between a genetic marker and disease into individual diagnostics and prognostics. And that is a challenge, I think, for years, if not decades, to come. One technology to get some more insight into that is again rooted in imaging, because most genetic studies only find an association between an alteration in your genetic code and the chance of disease. But now that we've found those locations, with imaging we can start to look into what is changing in the brain, and in this way we can shed some light on what potential processes can go on. This is a technology, it's called VBM, voxel-based morphometry. Basically, it's a technology that enables you to compare the density of cortical gray matter in different areas of the brain. It became very famous with a later, people later realized it was a flawed study, but it was a study in London taxi drivers. It was before, say, Bart's and my time, before navigation was there. You needed, as a cab driver, to have a very good memory, and they used these kind of studies to make the claim that actually the hippocampus of taxi drivers that were driving longer was growing with time. And they used that study for it. Now we use a similar technology now, but we use this technology to see if people have a genetic a SNP that is linked to disease, where are there differences in the brain between the subject with the SNP and without the SNP. And we've done that for 5,000 people for 19 SNPs. We put all these maps online, and this gives some insight in order to things that just used to be associations. We now know that apparently some changes happen in the brain because of this SNP. And this is one small step in starting to unravel the relationship between a genetic predisposition for disease and what is happening in the brain. And I think it's very useful to shed more light on brain disease development. I would like to conclude, and this is almost an introduction to the next talk by Bram van Ginneke. What we've been doing is a data science. We're collecting a lot of data, we're following patients over time, and we try to build diagnostic and prognostic models. Increasingly, this is a bottleneck because we have so many data, but in parallel, very powerful AI tools are being developed to deal with this large amount of data. Sometimes over-human quality are associated with these data. For example, this article by The Economist, anything you can do, I can do better, where I stands for artificial intelligence. And the question is whether we should embrace or fear it in clinical medicine. And I think we should embrace it, because I think the extremely complex relation between genetic data, environmental data, how it turns into what we look like, what we can see with imaging, and how we can help it to predict disease. In order to model this complex behavior, we need these very complex AI data science tools. In the end, I think this will redefine medicine. Medicine is really becoming a data science. I think the field of radiology will be one of the key leaders turning in the hospital into what I call a diagnostic competence center, where the key role is about precision medicine, doing individual diagnostics and prognostics. This will really improve our capability of doing precision medicine, but only if we embrace artificial intelligence solutions, because we have to combine information from different sources, and this is extremely complex. And because we're going to detect more diseases early, we'll also see an increase in minimally invasive image-guided interventions. So I would like to come back to our start. This is Bart and me. This was in 1993 when I got my master's thesis after he seduced me into going into the field. I did a happiness detector and I found two very happy faces on this picture. Interestingly, I also did a dream analysis. So I don't know for who noticed, but this is Gerard het Hoofd, but that's a few years before he got his Nobel Prize. So I think he was already dreaming about it here, but he was not really paying attention. So, and here's Bram again with Hetty. And this is then 5 years later. So I think he didn't really age a lot in those 5 years. And here, this is also next to the happiness detector. I think this was a nice picture. I could find this. I was actually quite difficult. This is really before the digital imaging, so I had to go through a lot of books to find all these pictures. But I now made it. But if you look and you enlarge, I mean, this is just a total happiness after you have brought a PhD student into the world. So Bart, thanks again. You really motivated me to start in this field. I've never regretted it, and I realize if I'd never met you, I would never be here for the two reasons I thought. So a lot of thanks to the people that were in this presentation, but the real acknowledgement of today is to you. Thanks a lot.
Thank you, Wiro, and thank you also for proving me right, that you do parallel Bart in enthusiasm for your work. And then the grand finale of today is Professor Bram van Ginneken. He graduated with Bart in 2000 on a project on screening for tuberculosis. And since then, he has continued that work. He has increased the scale of it, and he is rolling out the methodology in various lesser developed countries worldwide. On the side, he is a professor of medical image analysis at Radboud University Medical Center and head of the Diagnostic Image Analysis Group.
Thank you very much, Josine. And thank you, Bart, for inviting me to be here. I landed this morning in Brussels from RSNA, so I'm maybe a bit tired, but I'm very happy that I can give this talk here. You asked me to speak about computer-aided diagnosis and deep learning. I'm going to do that, but actually I decided to just talk about the project that you gave me 21 years ago when I started as a PhD student, and look a bit back on what happened in those 4 years and also what happened afterwards. And there will be a bit of computer-aided diagnosis and deep learning in it. So I was thinking, when did I first met you? What do I remember of that? I remember my job interview. You had a PhD position, which I found very interesting. It was about writing a computer program that would say of an X-ray whether there were signs of tuberculosis on it. And there was a company involved, and it sounded really interesting to me, but I wanted to meet this company and see it before I would say yes, because you said the company is very important. So I said, okay, let's visit the company. And you agreed. You took me by car all the way to Delft, and behind the central station in Delft on the other side was a really, really old factory. It was really quite a desolated area, and this is what I mostly remember from our first meetings. It was kind of an opening scene where we had just visited this factory, and weather was a bit like today. And we were driving back from the factory, and you pulled the car to the side of the road there in this industry area. And you looked at me really seriously, and I knew that you now wanted to have a decision, because you drove me all the way to Delft, and you were afraid that maybe I didn't like the project or so. So you put me under a lot of pressure. And I said, yes, I will do this project. I say here what Bart and Hans had planned. So Bart ter Haar and Hans Haarman, two Haars. Hans Haarman was the head of Old Delft, I think it was called at that time. And they had made a digital X-ray machine which they wanted to use for tuberculosis screening. So the two of you concocted this plan, and I decided, okay, I'm going to do it. So a bit of background. because this company was actually a very interesting company. It came out of NRAF, dat was de eerste Nederlandse röntgenapparatenfabriek. So they were the first company to build X-ray machines in the Netherlands. And in the 1950s and 1960s, they built this Odelka camera for TB screening, but also for general X-ray. And they actually sold over 25,000 all over the world. And some of them are still operational today. It's actually a big problem for this company. That camera was so robust and so sturdy that it wouldn't break. And then you can't really earn a lot of money as a company. And then you see, I think this is actually the factory where we were at that meeting. I'm not 100% sure, but they were making these cameras, really a lot of them, in the 50s and the 60s. And these cameras were super important for tuberculosis screening in Western countries, but also in developing countries all over the world. In the 50s and in the 60s, they were widely used also in the Netherlands. So mobile screening was actually implemented there with that truck. And you see the same guy on the picture over there taking a picture of somebody. And there's one really big drawback of this analog X-ray is that it's very expensive. These films are really expensive. So the moment that radiology digitized, actually the price of silver dropped because there's a lot of silver in these screens. And to make these films cheaper, they did what you see on that picture over there. They actually made very small films, 10 by 10 centimeters, and then put them on a magnifying glass, and this is how you would read TB screening cases and then fill out the results on an envelope lying there, and then you put the film in there. And I decided, okay, I'm going to work on this project, and we were going to use the new digital machine, and I would develop in 4 years, plenty of time, of course, I thought, a program that would detect tuberculosis. It's interesting, now we're 20 years after the opening scene. Companies now called Delft Imaging Systems, and they actually advertise their tuberculosis solution with the same old picture, from analog to digital X-ray. So what's the problem with analog? You have to use films, chemicals, that's labor intensive and expensive. And now we have digital detectors, no consumables, so no film is needed. And the other advantage that they now list 20 years later is Cut for TB. That's the commercial name of the program that we developed. And this is from their website. This is what they advertise now. If you want to screen a large amount of people for tuberculosis, you take an X-ray and perform the computer analysis, and then you decide which people have to cough up sputum for a much more expensive gene expert test. And this is the way to screen large groups of people with TB. And we have still 10 million people diagnosed with TB worldwide. It's in the top 10 of most deadly diseases, but it is a disease for which there is a cure that costs only $10. So that's really outrageous. We need to find these people earlier and make sure that they don't infect others and just put them on this cheap treatment. And it sounds like a really simple problem, but it has not been solved yet. But screening large groups for that X-ray is now seen again as very important. So I dived into that, and let's look a little bit at what we did in these 4 years that I had during my PhD. Now, this is one of the pictures I could find. I shared most of my PhD time in a room with Josien and Erik Meijering. And it was a very small room, but at someday we found a small couch that we managed to fit into the room, and we used that couch to read scientific literature, as you can see. And this is a picture of Bart in the same room in my office. And actually Bart's very important here, but there are also a few other really important things on this picture. So there's the digital or the analog X-ray light box, I have to say, because it turned out that throughout my PhD I didn't use any digital image. I get to that. That was a big problem. But you also see that cabinet over there in the corner. That was the TGV cast. So TGV was the name of Bart's group. It was Tools of Geometry for Vision. And in that cast cabinet, we stored every paper on this topic, mainly scale space theory. There was even a a typewritten manuscript of the structure of images by Jan Koenderink in that cast, so a museum piece. And I was given the task to maintain that cast. That was actually my most important task in the first period of my PhD. And it was a bit of a problem. The group was not totally what I expected. I expected I was going to develop this program to analyze X-rays, but I was having meetings with the TGV members, and we would be in front of a whiteboard, and people would write formulas and formulas and formulas on the whiteboard, and I didn't understand much of it. And they helped me. Luc Florac gave me a nice book on tensor calculus, which was really complicated. And I read in that book that Albert Einstein thought that this was not really necessary to have such complex mathematical notation. So I didn't really know whether I should continue with that. But I tried with these tools for geometry and vision, with geometric reasoning, as you called it, to build my first algorithms. But at some point I decided, yeah, that's not the way to go. I need a lot of images, and I need to do machine learning or pattern recognition, as we called it that days. But that was my problem. I didn't have any images. I actually had 4 films which were on that light box that you see over there, and Jan de Groot had scanned them for me, and these were the only 4 images I had in the first year of my PhD. I also found out that Bart had written this grant proposal for detecting TB in X-rays without ever having seen an X-ray with tuberculosis. And that's rare in the Netherlands, so he had that kind of a reason there. But so where was I going to get my images from? Well, through my PhD, there was a solution, because we heard that Delft now was going to sell a lot of X-ray machines in Brazil for a huge TB screening project, and there we would get our images from. And therefore, Bart and I had also to go to Rio de Janeiro to talk to the people there, even give a presentation to the minister. So we went there, and Bart immediately arranged, within a week, I don't know how he managed to do that, that he would give a course in Rio de Janeiro on scale space theory that lasted an entire week at some mathematical institute. So we were there for quite a while. For me, a problem was that I had to have a suit, because I had to talk to the minister. And you saw what I looked like in those days. I didn't have any suit. But Bart also solved that problem for me. He invited me to his house. And then Hattie came with a whole collection of old suits of Bart that I think she didn't really like anymore, because she tried to give them all to me. But I selected only one. It was a brown suit, and I looked really like the 1970s, and my mother really liked it. And we wore it in Brazil for the minister. And we had a great time in Brazil. We had an apartment right between Copacabana Beach and Ipanema Beach, and we would have cocktails every night on the beach under a coconut tree. It was absolutely fantastic. Only Delft in the end didn't sell a single machine there, so I still didn't have any image. So then I had to do something, and I actually went to Tilburg, where they keep all these 10 by 10 films of the refugee screening in the Netherlands. So they had huge amounts of films, but also not so many abnormalities. So I spent weeks there going through the reports. They let me enter their archive, selecting the envelopes with the abnormal images, which I then took back to Utrecht. And then at the radiotherapy department, they had a very good scanner. So I scanned all of that, and that's how I eventually got my about 1,000 images for the project. Yeah, so these are a few slides which I made at the end of my PhD. So there we actually we had the idea that the computer would kind of pre-select a set of normal images so that the radiologist would not have to read everything. The way the software is used now is just that people use the score of the software to determine who to do further tests on. So it's fully automated. And actually Pakistan, where you see the stamp here, is the country where we have the most installations now. So here you see these small 10 by 10 films with scanned with the regions of abnormality outlined that I was trying to detect. And this is my lung field segmentation that I was very proud of. It was super advanced technology at the time. It's active shape models. So these points automatically have learned what contour looks like, and then there's a global shape model. And Bart actually helped me. He outlined the lung fields in hundreds of images as a second observer in my study. I was also really happy that you did that. It was a lot of work. And then we had then I could divide the lung fields into regions, and I knew if these regions were normal or abnormal, and I computed features for these regions and then used the classifier. And this slide shows that I'm a real disciple of Bart, because I used a multi-scale filter bank of Gaussian derivatives for computing my features, and that's the kind of technology that our group swore by. And actually, we can now ask what happened next. This was kind of an okay system. It would work well on images, finding images with clear abnormalities, but it wasn't really that good, so we had to improve it. So I got my thesis, and then actually a problem occurred. We continued with the research. Julia Arjeva, whose thesis you also see here, continued with it. But all Delft went out of business because they weren't selling many of these machines. They were too expensive at the time. But luckily, in 2006, they came back under the name Delft Imaging Systems, led by Guido Geerts, who's in the audience here today. And now with a better, a cheaper machine and an integrated solution with a whole container where you could do the TB screening. And we got a new funding to get some of these units installed in Zambia and South Africa. And this is the one in Zambia, in the Kanyama clinic. It's a huge clinic. It's actually the largest clinic in the world if you look at the number of patients on ART drugs, so anti-HIV drugs. And they didn't have an X-ray machine until we got this funding. So this container was placed behind the clinic, and it's still operational today. And it really made tens of thousands of images that we could use for training the software. And we also had a new PhD student standing there next to the container, Laurens Hogeweg, who further developed the algorithms. So we then had a number of releases of the software over the years, and actually in 2015, with a few more PhD students who had finished and many more algorithms that we had developed, some of them integrated into the software, we also certified the software. Just to give you an idea what software is now doing, it's producing this heat map, or the regions that are red are abnormal according to the computer. And depending on how much red there basically is in the heat map and a couple of other algorithms, a score is computed. So this is a very abnormal image. It's another image with clear abnormalities and a very high score. And here you see that this is a version 4 of the software. It still was a bit sensitive to necklaces if people were wearing these. During my PhD, if somebody was wearing a necklace, my software would completely think this is TB. I didn't have enough data back then. But there's also quite a subtle abnormality in the X-ray over there, a bit behind the scapulae, and that's nicely picked up by the software. Here's another one. Another example of a bit more subtle abnormality that's also detected. So these images get a score above 50, which is typically what you would use as a threshold. And then the normal images sometimes have a bit of false positives with overlying bone structures, but usually they get a much lower score. So then we decided to move the maintenance and further development of the software to the company that I had started in 2014, Tirona. And two of my former PhD students, the last one doesn't have a thesis yet, so I just put his face there. He moved to the company before finishing his thesis. He said it was almost finished. This is something I've learned: never let your PhD students go to a company until the thesis is completely finished. But it's almost finished now. That's Rick. And Jaime and Rick further have developed the software and really have much more data now, and also developed a solution around it that we call Cat4TB Cloud and Cat4TB Box. So this is the Cat4TB Box. It's just a small computer, and basically you place this computer next to an X-ray machine, and it does all the computations, and it's also a web server, so if you're remote from the internet but within Wi-Fi reach of that computer, then in your browser you can browse all the images and then look at the heat maps and see the scores. And if the computer is connected to the internet, then it's Cat4TB Cloud. You can upload, the images are automatically uploaded, and you can basically read them from anywhere. You can also give the people who get the picture a code so that they can watch the image on their own phone, because you don't print it on film anymore. People like to show the picture to their family physician, for example. So that works really well, and people are very enthusiastic about this solution. And we have already 24 countries where we now have installations. We have in total now, I think, close to 150 installations. So it's going extremely well. There's a lot of interest for it. And There are a few really big screening programs that are using a lot of these boxes because that's the only way they can screen a very large number of people. If you have to have human-trained readers on site next to the X-ray machine, that's just logistically very hard to achieve. And now you don't need that. You just need somebody to operate the machine. And within a minute, you will know whether this person has to give up sputum or not. So then with limited sputum capacity and one X-ray machine, you can screen very large amounts of people. And this is an example of how it was done at a prevalence survey in Gambia with mobile units. They set them up in some school or some local building, and then they screen the population. This is a big prison screening in the Philippines, where they have a very luxurious touring car with donor money that drives around between prisons and remote areas and has an X-ray machine in the bus. And this is an example from a movie that Delft Imaging Systems also put online of a clinic in Dhaka in Bangladesh, where people go and you can see the ID, they get the X-ray, the score of the software determines who has to cough up the sputum, and then it goes into these blue boxes and into the expert machine. And then within 2 hours you know if the person has TB, so they can wait for it and you can immediately start the treatment on the spot. Okay, so what's next? I also have to talk about deep learning. Deep learning is now really at the top of the hype cycle. So I just came back from RSNA, and there you could get ribbons with deep learning on it if you follow a little course as a radiologist, and then you are certified for deep learning because that's the technology you need to master these days. Well, in our group, we have used deep learning and started to get good results really in 2014. That also really impressed me. 2013, I wasn't too impressed, but it takes a while to understand how to train these networks. And actually, I trained very similar networks while you were giving your course in Rio de Janeiro. I was using convolutional neural networks then in MATLAB, but it didn't really work at that time. But if you do it right now, with deep learning, you can train everything from image to final score. So also the features that you compute, you no longer have to think of them yourselves, but you learn them from the data. And in 2014, 15, everybody in our group, one by one, converted to deep learning, so we're only using deep learning. And next year, the deep learning version of CAT4TB, early next year, it's ready now, but early next year we plan to release it. And okay, this is a boring slide with a big table, but for me, this is really, really impressive. This is some confidential, this is our own internal data we have at Tirona that we only use for validation. So you see the results here from CAT4TB from version 3, 4, 5 to 6. 6 is the deep learning one that we are going to release. And version 3 was the first one that could handle images from any X-ray machine. And these are 18 data sets from 15 different X-ray models from different countries, different manufacturers. And we've all very carefully read these images 2 times according to a very strict reading protocol. So we have the area under the curve in the final column of the second observer. And you can see that basically version 3 wasn't really good yet at dealing with all these different X-ray machines because that was our first version trying to do that. So from 3 to 4 we made a big jump. From 4 to 5, we improved classifier further, used more data, various other tricks. And for some machines, it's got quite better. So on average, we went from 0.869 to 0.923. And now with deep learning, we make another big jump to 0.965 area under the curve. And that's actually, yeah, within the margin of the second observer. It's actually a bit better than the second observer that read the same images. So I'm super impressed by this performance. This basically took me a bit more than 4 years, unfortunately, but I think we can really be proud of this achievement. So that sort of brings me back to this. I think, Bart, I didn't finish it in 4 years, like I promised in the car in Delft 21 years ago. But in the end, I think the project is super successful, and like Viro also said, if it wasn't for you, the project would not have existed. Not only because you wrote the grant without having seen an X-ray with TB, But also, throughout my PhD, you were always enthusiastic. I mean, it wasn't very easy what I was trying to do, but always when I was coming back from a meeting with you, I was full of energy again and believed that we could do it. And you really supported me in all sorts of ways, and that was very important for the project. And the other reason is that I put this as the final picture, is that we have kind of come full circle. So you have the TGV-kast there with these geometrical reasoning approaches, rule-based schemes, that I think still the group in Eindhoven is using quite a bit. We left that, and I thought we really need to do machine learning. Now that has become deep learning. But from what I've understood from you is you want to now close the circle again and really try to understand what is deep learning doing and what is the connection to these tools of geometry and vision. And we know that these connections are there. So I think this is an absolutely brilliant idea, and I'm looking forward to what you will say about this in the next lecture that we get today. Because one thing I'm really sure about is that you will not retire, and you will just continue doing fantastic work. Thank you.